Hello Chem 1A, this is Chapter 3, Lecture Video 9, and we're going to be talking about empirical formulas and how to determine them from percent compositions, as well as how to distinguish between an empirical formula and a molecular formula. So an empirical formula shows the simplest ratio of atoms to one another in a formula. This is how we show all ionic compounds, but molecular compounds aren't necessarily given by the empirical formula. They're more often given by their molecular formula. So an example of this could be with C2H4O2. This is a molecular formula. It shows that there are exactly 2 carbons, 4 hydrogens, and 2 oxygen atoms in every single compound or molecule that makes up this compound. However, the empirical formula of this compound would be the simplest ratio of elements to one another in the compound, or in other words, CH2O, because we can divide all these by 2 to give us this formula. This formula is known as the empirical formula. All ionic compounds are always represented by their empirical formulas, and that's why we always go to the lowest ratio of elements to each other, or ions to each other, in the ionic compound. Molecular formulas are different in that they show the exact composition of the molecule. The molecular formula is by far the more valuable of the formulas to have, as it tells you exactly how many atoms of each element are present in the compound itself, in the molecules. However, sometimes we don't have enough information to determine our molecular formula, or we need to determine the empirical formula first before we can identify the molecular formula. So let's talk about how to determine an empirical formula from, specifically, percent composition, which is a topic we talked about in the last lecture video. So we can calculate percent composition from a molecular formula, as we saw in the last lecture video. However, we can also do the reverse. If I'm given percent compositions, I can determine the empirical formula for my compound. The first step would be to write out our compound's formula using variables. So we're going to do an organic compound that contains carbon, hydrogen, and oxygen in our example. And we're going to go through all the steps first, and then we'll do an example. So in our case, we're going to say, hey, we have CX, HY, OZ, and our goal of the problem is going to be identifying what X, Y, and Z values are. The first step, if you're dealing with percent composition, is to assume that you have 100 grams of the compound. Now, you don't necessarily need to assume 100. You could assume any amount you want. However, if you assume 100 grams, then whatever your percent composition is, that's how many grams of that element you have. If you choose a different number, you're going to actually have to calculate what percentage of that mass you assumed is each element. So step 3, if you are assuming 100, each gram amount is equal to the percent composition for that element. Next, we're going to convert the mass of each element that we determined in the last step into moles by dividing by the molar mass of the element. After that, we'll plug in our mole values into our formula. So whatever moles we calculated for C, we'll put that in as X. Whatever moles for O, we'll put that in as Y, and H as Z. The second to last step here is going to be to divide all the moles by the smallest mole value. So whichever one of these values that we plugged in here is the smallest, we'll divide all of them, including itself, by that mole value. Sometimes this is when our problem is completely done. Other times we still have one more step to go after that. So sometimes if the ratios of this division in this step end up being fractional, we need to multiply by a value to get rid of them to give us whole number values. And in this step, sometimes we have to do it, sometimes we don't need to. It's really just dependent on whether we get fractional values in our answer after step 6. If you do all this out, you would now have determined the empirical formula of the compound. So let's do an example problem after this slide. The relationship between a molecular and empirical formula is important as well. We know that whatever our empirical formula is right here, if we multiply it by some integer whole number value, we're going to get the molecular formula. However, I don't know what n is necessarily, so we need to find a way to determine what value to multiply our empirical formula by in order to determine our molecular formula. N we know has to be an integer, has to be a whole number positive value. The way we can calculate this is we can use the molar mass of the molecular formula and divide it by the molar mass of the empirical formula. But we can only do this if we're given the molar mass of the molecular formula. So in a problem that you're given the molar mass of the molecular formula for, you can actually determine the molecular formula after determining the empirical formula, because if you know the empirical formula, you can get its molar mass. Divide this, that gives you N. You plug N in, and that'll get you your molecular formula. We're going to do this in the next problem. Okay, so let's do an example problem. What is the molecular formula for a compound that is 41.87% carbon, 2.34% hydrogen, 5.79% oxygen, and has a molar mass of 430.2 grams per mole? So here we need to first assume a mass of compound. I'm going to assume we have 100 grams of compound. This makes my life somewhat easier, as that tells me that I have 41.87 grams of carbon, 2.34 grams of hydrogen, and 55.79 grams of oxygen. I can then use the molar masses of each of these, 12.01 for carbon, 1.01 for hydrogen, and 16.00 for oxygen, to get moles of each of these values. That's the next step. The primary thing we always need to determine in order to determine an empirical formula is moles of every element in the compound. And this is how we get to that value from percent composition. So let's calculate these out. Okay, so these are the values we should get for our moles of each element. All right. Now that we have these moles, we need to determine which one is the smallest number. And in this case, as we can hopefully tell, it's hydrogen. So I'm going to plug these into my formula that I have, CxHyOZ. And we're going to get, hey, carbon is 3.486, hydrogen is 2.317, oxygen is 3.487. We're going to divide all these by 2.317. And this will get me this result. So as you can see, we can kind of round these a bit, right? So really what we have is carbon 1.5, hydrogen 1, O 1.5. Now we do have fractional values here. We cannot round up 0.5. So we need to find a way to do step 7 in our list of things, which means we need to multiply this entire formula by a number that will get rid of our halves. Well, how do I do that? I need to multiply the whole thing by 2. This gets me carbon 3, H2O3. And this is my empirical formula for this compound. Now, after getting the empirical formula, I want to calculate N, which N we know is our molar mass of the molecular formula, which we're given 430, divided by the molar mass of this empirical formula, which we can calculate by just taking the molar masses of carbon times 3 plus the molar mass of hydrogen times 2 plus the molar mass of oxygen times 3. And we should get 86.05 grams per mole. This is our molar mass of this formula here, our empirical formula. Now, if we divide these two values out, we get, or should get, a whole number integer, or something very, very close to a whole number. And if you don't, that means somewhere along the lines in the determination of our empirical formula or its molar mass, we have messed up. If you do this calculation out, you should get 4.9994, which effectively is 5. This gives me my N value. Now I can get my molecular formula, because my molecular formula is going to be equal to my empirical formula times N. So C3H2O3 times 5, the N value. This gives me C15H10O15 as my molecular formula of this compound. All right, so if you guys have any questions about this, this is some of the harder stuff in chapter 3. Please let me know. I'm always there to help you guys.